did you bring? Huh? Snacks? Tonight one. Oh. Okay. 今天没有塞车啊？今天没有塞车。哦，可以现在。那早上我们家里有。啊？hello hello hello，真小声的。hello hello 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 hello， 有声音吗？有啊，有声音。哦，你们听得到有声音？我没有听到。hello，够大声了，够吗？hello hello 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 hello， 有声音吗？有啊，如果你们听到就 OK 了，要整整对着。OK，let's start. So today I'm gonna continue with the last example we left about topologies in curve, sine curve. Okay, so this curve we seen here. Sine curve, curves or curve. Okay, so what this topology sine curve here? So let's draw it. Well, we start with y equals to sine 1 over x. If you remember from your MA, right? This is one of the curve that you cannot remove singularity or cannot remove discontinuity. Yeah. Okay. Which well, it is not just a discontinuous, right? Actually, it doesn't define at a point. Okay, there's one point that is not defined here. Exactly is the point where x equals to 0. And because 1 over 0 is undefined here. So how about away from 0? How does this curve looks like? This is sine of something, right? Sine is bound between 1 and -1. Okay. So actually this curve, right, will go really frequently around 1 and negative 1. Okay, get more frequent when it get to 0. Okay, similarly, you can draw a similar picture on the other side. Okay, but let's just focus on s greater than 0. Okay, you might hope that if it's not defined at 0, we replace it or not. Okay, because we have another example last time, right, where we also have let's say sine times sine over 1 over x, that this curve, right, it get really small, okay, when you get to 0. It's not defined as 0 also because sine 1 over 0 is not. But for this curve, right, you can see that the oscillation, okay, or the amplitude of this curve, right, getting smaller and smaller actually. They eventually converge to 0. So for this case, actually, we can tune it in. But if you look at this curve here, what's the limit point of this curve? It doesn't have a limit to when x goes to 0, but it has limit point. And limit point is different, right? Limit is about convergence of sequence. So there's a limit point which you can consider open neighborhood, okay, around your limit point. So if you notice, right, you could pick any point from this y-axis here around -1 and 1. You pick any point here, okay, you make a bow around it. It should intersect with your curve of y equals to sine 1 over x. And no matter how small you make this open bow. Okay, does it make sense? Okay, so well, if you make this bow around smaller, right, there's some yx stay around here, then you need to show that you can solve it using this y equals to sine 1 over x. Not for all the yx, but there's some point on this graph here, or if we want to use language from algebraic geometry, right, the zero set, okay, zero set of this y minus sine over 1 over x here will stay inside any open neighborhood you make around this interval of 0 cross minus the closed interval from -1 to 1. Does that make sense? Make sense or not? Okay. So last time we claimed that these two pieces here. So these two pieces here. So let's say S is this guy. Okay. So union with the this guy union with the limit point of x, which we call the x bar here. Okay. Is connected, but not half connected. Okay, I want to show you this proof here, because when we show not half connected here, we're going to use a very sophisticated theory from MA. Okay, we want to see it from a sequential continuity point of view, and then you will see how intermediate value theorem get used here very nicely. Okay, first, why is it connected? How to see it's connected? Oh, okay, sure. Yeah, you can do that. Okay, but yeah, you can do that. I urge you to try it. But there's an easier way. There's an easier way. Why is it connected? There's an easier way to see why is it connected. Based on what we have proven. You can prove from the definition, that's fine. How about use what we have proven? For example, product of two connected set is connected. Closure of a connected set still connected. You combine these two or not? Like Darren exercise, right? I give you all the theorem put together. Okay, what do you know that is connected now? How do you know it's connected now? So how do we view this graph here? So let me move this down. how do we really write down the point in x actually? How do we write down the point in x? So the point in x, you can parameterize it, right? How do you parameterize it? And based on this implicit function. Okay, how to parameterize it? Your x coordinate is what? X, just x. Y coordinate, sine 1 over x. Okay, for x squared. Okay, union this limit point here. So limit point here is 0 cross close interval -1. Okay, so you check. This is a product set. Okay, if you want to show that a product set is connected, one way is to see that each component is connected. Okay, each component is connected. This component connected or not? What is this component here? X greater than 0. Is it connected? Connected. Okay. From the open set point of view, this part, sine 1 over x, connected or not? Huh? Connected or not? This line here, connected or not? Okay. So you can easily show that these two lines should be connected. If you like, right, maybe you want to show that this is an image of a connected set. So it's connected. Continuous image. Okay, so this function is continuous. Okay, continuous image of a connected set is connected for this one. For the whole thing, you can do that. But right. So first, let me write here. S is connected. Okay, S it is a product of two connected sets. So last time we proved that finite product, right? Finite Cartesian product of connected set is connected. So to argue why those two components is connected. First component, I think straightforward, right? It's just a real positive real number line. But the second component is connected. Why? Because it is the continuous image of a connected set. Last time we proved that intervals are connected, right? Okay, so this connected set actually is going from open interval 0 to infinity. Okay, then we also prove that anything in between up to the closure, right, of your connected set should be also connected last time. If you remember, I drew an open ball in a closed ball. Okay, all of everything in between, adjoining in particular, adjoining limit points to connected set is still connected. Okay, so it is connected. Now we are going to show that it is not path connected. Path connected means what? What does path connected means? You need to be able to connect by path. But what's the definition of path? Connect what by path? Any 2 points, right, inside your set. But what is path? Yes, function, more than function, right? Continuous function. Okay. So if set is path connected, any 2 points you pick, there must be a function. Function from where? From the interval of 0 to 1. You can think of it like a time interval. Okay, maybe you might ask me, hey, why I must start at 0 and stop at 1? No, you can actually start at any A and B, but you can, after rescaling, it's just 0 to 1. Okay, so we might as well just think of it from 0 to 1. Okay, 0 to 1, you have a line, okay, and then you map into your space. Okay, does it make sense? So it's like you want to think of it, your watch, right? The time is like linear. Okay, no matter how fast you move, how slow you move, right? The time is just same speed, same tempo. Okay, but the way you move inside the space, right? is quite different than how the time moves. Okay, so you want to use your time uh, to to record your movement. So this is path. So to show that it's not path connected, what do you do? What can you do? Joshua, to show something is not path connected, what can you do? What what do we do? Oh yeah, sure. So before that, even before that, why are we doing that? Well, how do we answer this path connected problem here? Mm. Yes. Okay, so you want to show that there's no continuous function, okay, from the closed interval 0, 1 to x. Okay. So to do that, suppose you have one. Okay, then you can always find you will always find two sequence, okay, that converge to different point, two subsequent. Every sequence, yeah. Is it what I say? Am I right? Saying. So how to show one function is not continuous? In particular, we want to show it from the point of view of sequential continuity. So sequential continuity says what? So, yes, correct. So if two sequence for any for any sequence that converge to x, right, then f of that sequence should converge to fx also. Okay, so if you can produce two sequence, okay, that converge to the same point, but f of xn converge to different point, then this function is not continuous. Okay, so let's say for sake of contradiction, okay, suppose we have a continuous function, okay, into S bar here. Okay, so I want to, since we suppose it is path connected, right? Might as well pick a point from X bar here. So let's pick the origin, okay, the 0 point here. The origin and any point in X. Okay, so where's the picture here? Sorry, let me bring the picture first. I think I will use this picture to talk about the proof. So let's pick this 0 point here and somewhere around X. Somewhere. Okay. So, well, well. So if you consider uh this function at any time, right? Okay, function at any time. How does this ft looks like? What's the image of ft? The path lying inside x bar, right? Okay. But you can see that okay, most of the point here. So let's write it at st and yt. Okay, st and yt here. So we get this. Then we will set our starting point at 0. Okay, so this point is t equals 0. And for t greater than 0, we will have xt greater than 0. Okay, and yt equals to sine of 1 over xt. Okay, so meaning what? Meaning for t greater than 0, we have points on this curve here. Make sense? Okay. Don't ask me why I cannot pick these points, because these are not the space we consider. Okay, we are just consider x bar here. Okay. Okay. So from here, can you see two sequence that doesn't converge the same point? Remember, what's this point we are considering here? What's the point we are considering here? What's the contradiction we want to get here? So we already make x and y in the function of t. Okay, so x is not the sequence you are caring about. You are caring about this t actually. So when t converge to 0, can you find two subsequence that converge to different points? I mean, after applying your f. Hmm? Jingsen. 1 and -1. Okay, so if you see that when our time are close to 0, right? Okay, but still, this yt here still get very close to 1. Still can get very close to -1. Okay. So how do we really say these things here? So let me write down the claim here. Claim, we will show that there exists Tn. Okay, we want to find a sequence, okay, that converge to 0 such that y of Tn is equals to -1. Okay, so we want to find this special sequence here. This sequence that its y value doesn't give you convergent sequence. Okay, so how do we do this rigorously? How do we do this rigorously? Okay, so once we get this, so let me write down what we get this. So then uh, y of Tn, so this sequence here does not converge. Okay, contradicting the continuity of. Okay, if you like, actually we see this f as a product function. Okay, product of function. Okay, so one component is not continuous, then the whole thing is not continuous. Okay, this is the part when we do continuous function, how we construct continuous function last time. Okay, so how to find this Tn? From this picture, can you tell me from this picture, how do you find it? Okay, good, good. So where the point there where you get sign of something is minus 1 and 1, right? Okay, but from this picture, you can see that they are just these peak here. Okay, so these are the sequence you are interested in. Okay, but this sequence here, we are checking it based on this xt, right? Okay, so how do you argue that you have this T1, T2, T3, and so on? Okay. X is continuous. X is continuous. Yeah. About right, about right. Yes, about right. So how do you put these things formally? Right? You are right, you are right, you are right, you are right, almost right. Okay. So to construct these T, right? Okay, let me write down the recipe. So first step, to construct this Tn, okay, so given n, we should able to choose all these un, u minus 1 here. Okay, later I will plot for you what are these un, ui, such that this ui lie between 0 and x of 1 over n. Okay, such that sine of 1 over un equals to minus 1n. So from here, what can you see? What's this point here? 1 over un. Our function is 1 over xn, right? Okay, so this un is some xn here. Okay, so meaning these are the peak that we are referring just now. So we are picking this peak first. U, for example, here is u1, u2, u3, u4, u4, u5. Okay, u6. Okay, but there's a controlling factor here. There's a controlling factor here. What's this controlling factor here doing? X of 1 over n. It depends on what this function have. Where is S1? Maybe, okay, let me do here. Maybe your X1, ooh, maybe your S1 is here. X on the times 1 is here. Then your U1 must be pushed to here or any of these. Okay, and then where is X half? Okay, then you control what's the next UI you need to take. Okay, depend on this xi over n, right? Not all the peak you need to pick. Okay, it's restricted in between x of 1 over n and 0. Okay, but this makes sense, right? Huh? Yeah. Ah, t. Yes. Function of t. Yeah, and then we make a sequence in t. This sequence in t converge to 0 when n get large. So that means when time getting smaller and smaller and smaller, this st is getting closer and closer and closer. When this st getting closer and closer and closer, then the ui your peak also closer and closer and closer. Yeah. Hi, Adrian. Can repeat what I say. When t get closer, my un get closer. Okay. When t get closer, When t get closer, my xt get closer. Or more precisely, when n get large, nt get smaller, time get smaller, xt get closer to 0, un also get closer to 0. Okay, so un get closer even faster than xt here. Okay, makes sense, huh? Okay. But another thing we need to make sure is this un is actually giving our this alternating sequence. Okay, we don't simply pick point from the curves. Okay, and then anything else we need to do? So now we already found this here 招生很重要哦，现在招生. So how after we found this UI, right? How do we found T? How do we make sure that there's a T that realizes this UI? 这很重要啊！你昨天不是要解一题？你不是要解那题？这么在一个圆的 boundary 上面可以找到 interval。你看这个也是圆圆的，圆圆的。然后在一个直线上面找一个点。好啊。So we know got this UI already. Okay, but why got the t that realize it? Why is, you see, you see, this un is bound between these two numbers here. Why this un can be realized as one of the time? What's the theorem that tells you that if your number lie between two things, you can hit it with your function? Intermediate value theorem. When can you use intermediate value theorem? When your function is continuous. Our x is continuous because we assume our f is continuous. Okay. So here, so two. Since f, our function on this connected set is connected, okay, by IVT, we actually can find some Tn in between 0 and 1 over n such that S of Tn equals to Un. Okay, very nice. Okay, does it make sense? So this really reflects how we find this function. I mean, find the sequence on this this x here. First of all, we identify the peak first. After we identify the peak, we show that there is a t that realizes this peak here. Does it make sense? Okay. Okay. 什么？大于 Tn. No, 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 no. So this is about time. Okay, so this is about t. This is about x. After we got point in x, and then we find what's the t that realizes x. Okay, does it make sense? Yes. Yeah. How to say this thing? How to put this? Yeah, I mean, sure, but so one thing I want you to notice is because you want to find a when okay, you are right. You are right in the sense that this x here is dependent on t. So if you give you one t, you'll get x. But before finding this t, right, how do you find this x? Meaning, how do you know what sequence that can produce me alternating 1 minus 1? So meaning, if I don't let you see this s first, hey, go and find t. Find the t. How to find? Correct or not? How to find a t that gives me alternating? You still need to check your x. You still need to check what x that give you the alternating first. If you straight away go find t is like this, right? So many t, go find. Go find the t that give me minus 1 and 1. How to find? I need to know that which t that can give me the s that such that my y has the alternating 1 minus 1. So you cannot avoid looking at x first. Does it make sense? Otherwise, you just blindly check. Just now we are not blindly check. Just now we say that we want this x. Okay, and then I argue you why that these x can be realized by some t, by intermediate value theorem. Okay, no, I don't care this. I don't care this ui correspond to what t, It's just some value that given by intermediate value theorem, but that's fine. As long as you prove it exists. As long as you prove it exists, and then with this property here, you can see that actually this Tn is getting closer, closer, closer at 0. It's not out of control one. Okay. Because in principle, intermediate value theorem, right, might give you a different T. In general, I might give you a different t. Okay, but in this case here, we have some restriction. Okay, make sense or not? Got question? Got question? Okay, I think this is a pretty good example on how we use IVT. Okay, yeah, very convenient one. Okay, because in real life, in practical life, I gave you a random UI here, right? I guess it's really hard to find this T. It's quite hard. Well, I mean, at least one of them you need to use calculator or sine inverse. You cannot choose by hand, right? And then you want to invert it some more. So it's quite computational heavy. Yeah. Unless you want to get a numerical value, but for us, we just need existence of sequences. Okay. All right. In that case, I will mention slide a bit on locally path connector, and then we'll move on to compactness. Okay, so before we go to locally path connectedness, the last thing we want to define on this path connectedness is about path component here. So basically, you can show that path connectedness is an equivalent relation. So meaning what? 2 points are equivalent here as long as they can connected by path. Is it true? So if you can connect to x, can you connect x to x itself or not? By constant loop. Okay, it's continuous constant path. And then if you can connect from x to y, can you connect back from y to x or not? How? Yeah, inverse. Inverse. Let me think. Inverse. Is it the right word or not? Inverse. Yeah, it's not quite right word, because we are not, we are reversing the path, but we are not taking inverse of that path. So we need to define properly what's the inverse of path here, right? Okay, so if you like, you can come to algebraic topology lesson. Okay. Yeah, we will do composing path. Okay. So but the inverse here is like taking the reversal orientation. Okay, reversal orientation. So meaning what? So meaning, hey, did I write it down? Oh, actually I do write it down here. Okay. So if you have a path that connect x to y, right? So f0 is x, f1 is y. Then how do you switch the endpoint? How do you switch the endpoint? Okay, use this new parameterization here, 1 minus t. Okay, what does 1 minus t do here? Your time reverse minus t. But when you do minus t, right, your 0 to 1 becomes what? Minus 0, minus 1, right? But we don't want that. Okay, we don't want that because our f is not defined at -1. So instead, what we do is we plus 1 to it. Okay, so that 1 minus t of every number here still live in 0. But this does do the job that we like. Why? If you put 0 into here, what do you get? F1. The point that originated at 0 and that started, sorry. The point at F1, so the ending point, become the starting point. But if you put t equal to 1 into this new function here, you get F0. Okay, so you go back. When you end, you start with the starting point. So you end with the starting point. Okay, so it swap the orientation here. Similarly, you can compose path. So composing path here, what's the technicality here? Sure, okay. If you see from the picture, right, you just draw, you can compose. But the point here is our path is only defined from the interval 0 to 1. So you have two intervals from 0 to 1. How to make it 0 to 1 again? Okay, so how to make it 0 to 1 again is I speed up. Okay, on the first one, I speed up by half. Sorry, I doubled up the speed. Okay, so two times 2t. Then 2t on this domain here can cover the original 0 to 1. Can or not? You try. So you put 0 into here, you get 2 times 0, 0. You start with 0. 2 times half that is 1. So you finish the whole part, the first half there. So if you remember from your calculus, right, this is just called a reparameterization. Okay, so this is just the speed and 2t. And then how about the other one? The other one is also speed out by 2t, but I shift down by -1. Okay, so that it matches up the domain. Okay. But this one is not in our scope. I don't require you to do this in this class. But this is the starting point of algebraic topology. Okay. And also this locally path connector is not in your exam as well, but I want to mention about it. It's in your textbook actually. So that's a very good point why I mentioned about it, because later I will tell you what's the relationship between locally connected or path connected with path connected. Okay, so what does locally path connected means? So locally connected at a point X, it means that if for every open neighborhood X, there exists a connected open neighborhood, another connected open neighborhood, okay, within U. So meaning it might not be connected in U, but you can found a smaller V inside this U such that it is connected there. Does it make sense? So let me draw it. So if we say that it's locally connected, right? So when mathematicians say locally, you need to localize to some point here. Okay, let's say this is X, localize at X. Then for any open neighborhood here, okay, you can find some connected neighborhood, maybe smaller, maybe the same, okay, uh, but inside here they are connected. Okay, so meaning you cannot split it into two parts of component set. Okay, for every. So if this set, this space is locally connected, then it is, if it is locally connected at every point here. Similarly for path connected, you just set a path connected adjective to your open neighborhood. Okay. So well, you might curious, why we do this definition here? Obviously, obvious what? Or this example is not obvious. So maybe you can find that some set is connected but not. So sorry. Connected is must be locally connected, but maybe you can find some set that is locally connected but not connected. Okay, otherwise, this definition is useless, or they are equivalent. Okay. This example is not good. Okay, not good. It's okay. It's just trying to show you something is locally connected, but it doesn't show you why we need these two different definitions. Okay. Okay. So what's the relation with what we know last time is if a topological space is locally connected, okay, if and only if for every open set U in X, each connected component of U is open in X, okay? So if you combine connected and open together, then you can show that this space is locally connected, okay, for this part here. Basically, do you understand what this theorem trying to say here? Because just previously, when we define locally connected, right, we say that for every open neighborhood, we want to find another connected. Does it need to be open? Yeah, connected open neighborhood that contain X that contain in V U. Okay, but now if you know that for every open set of U, each connected component of U is also open, then you can check that this topological space is locally connected. So the last one is what you can show is every path connected component here will lies in a connected component of X. So, okay, this two line here, you know what's the difference between path component and connected component? What's the difference? What's the difference? What's the difference? Path component means the connected component that you can join with path. Right? You can, because just now we showed that not every connected space is path connected, right? Okay, so you could have a path connected component, you could have connected component. They might be different. Connected doesn't imply path connected, but path connected implies connected. Okay, so the path connector must live in some of the connector component. Yeah, because if it is path connector, it must be connected. Okay. And then if X is locally path connected, actually the connected component and path connected component is the same. Okay, so meaning what? Meaning if X is locally path connected, these two are equivalent. Connected imply path connected imply connected. Or when is it true? When your S is locally path connected. So this is why in real number, right, you can either use connectedness or you can either use path connected because it's equivalent, because this set is locally connected. Okay. Okay or not? Huh? Okay. Does it make sense? Okay, so this is when connectedness and path connected are equivalent. Okay, when the space is locally path. Okay, any questions so far about connectedness? Any questions so far? Okay. Okay, before we take a break, right? So let's motivate compactness, and then we will left the definition of the break. So let's do motivation first. Okay, so first of all, we say that X and Y are topologically equivalent if there is a homeomorphism between them. Okay, meaning we can transfer open set from both sides. Okay, U is open if and only if FU is open. So last time, what we established was the open interval 0 to 1 is not homeomorphic to the closed interval 0 to 1. Okay, how do we show this? Okay, we show this by if we delete one point. Okay, so if we delete one point from one set, if we have a F that go between them, okay, we delete one point from one set, and then we delete another point. Okay, so we delete another point from the other set. if you can note here that the point I delete on the closed interval here still make this half closed interval here connected. But if there's a homeomorphism in between them, the image of this homeomorphism must be connected also. Okay, but if I delete one point here, where should this image lie? This is an open interval. Okay, so meaning my image must lie in between 0 and 1. So once you take one point away from this open interval, then this open interval becomes not disconnected. Okay, so this will contradict that continuous image of a connected set is connected. Okay, so this too is homeomorphic, but can you always use this way? Okay, can you always use this way to show that two things is not homeomorphic or not? Does this strategy always work or not? Okay, for example, can you use this strategy? For example, okay, does this, okay, so let me write here, does this, we call it cut point, right? Does this cut point strategy always work? Okay, meaning to check whether two set are not homeomorphic. Does it always work or not? Okay, so let me give you another example. So how about open ball and a closed ball? Is this two homeomorphic? Can I use cut point to decide or not? If I cut one point, just now cut from boundary, I also cut from boundary in this case. If I cut from boundary, open ball, where's the point removed? Remove one point. So okay, let's draw it. So if I remove one point from the boundary here, then because it is open ball, right? So I must remove some interior point here. Connected or not? Still connected. Oh, 你不甘心，再 remove 一粒，再 remove 一粒。Connected or not? This space still connected or not? 不甘心，再 remove 一粒。How much how much point you want to remove? Until you can see. Okay, so next up we will introduce the more sophisticated notion to talk about these, which is compactness, and also invariant under homeomorphism. Okay. Okay. So let's break until 11:01. 哎，中医没有在啊？中医啊，没有在睡觉。有考试没？没有考试，考完了你们。哦，你们考完了，你们少考试是吗？哦，两个。我知道你们有考试。也是其中一个原因啊，也是其中一个原因啊。对啊，今天不准备发，因为也是怕等下没有人。对啊，你们不是考试吗？哎，那个是常识吧，不管好还是烂都是差不多。批完了？对啊。哦，好嘞。那我想把你平均分多少吗？有。现在要讲？对，就是，我只是好奇哦。我只能说又是一个破纪录吧。高的记录还是低的记录？那我发给你。嗯。 艾瑞，这是你的伞嘛？那前面那个是你的伞嘛？挂了。
不是，我那把长柄伞今天早上也跑。确实，我的伞比较容易坏，是吧？没有那把长柄里面坏了。他今天早上刚刚爆，我对啊，不过那把本来就是我捡来的，所以也没什么太大问题。对的，对的，都不用追那个小铁的点大，那就容易。手话干嘛到？我记得昨天偏还对，我昨天跑偏。对啊，上升就是凡尔赛。对啊，上升就是凡尔赛。
可以，你跟他赌，就是赌博机他考多少？跟他赌，你跟他赌。
他敢赌的，你看都敢赌的，我看。
那是哪一个上分嘛？
他们说，
你看，
没有你可能在
他超选走哦。
还有什么？还有什么？对，等一下，我们要糖。哪一个？从哪里开始看？
从这里看。
你知道被他虐待啊？
什么
？S up 506有没？
上去了呢？
讲啊，做考试的人做啊。
我觉得到时候等
他的考试要3个钟哦，我还能做2个钟哦。我认送完了没有时间，
我不发表评论。
他考多少？
考完没有？我等明天出来的时候，就要等你家来问我，不是考挺差，所以你明天准备考去？
明天判案。
OK。哎，我有看到有什么能透露的数据？
没有。
好吧，太过分了。
喂，怎么这样子？
不满足一下大家。有没有追那个是不是有些？
当然啊，
有啊。
你要讲，
你要承认哪个是你写的？
你应该猜到是吧？
我猜不到。
啊，那就算了
啊，算了。明天我们一起讨论啊，我们2份考试一起讨论。啊？什么？哦，你看 Line。哦，对，好像是。
好像也不能
看 Line 不一定啊。
不一定哦。
哎，一定嘛，一定嘛，一定啊，一定，因为它 continuous 嘛。你如果假设你看这条，它这条的话，它应该是 OK 有一个 with 哦不 OK， 你要 argue 是说为什么你这个东西的 image 不可能是一个点线，因为它可以吗？它可以是一个点吗？应该是不可以的。如果它不是点的话，它应该就要长这样的东西了。但如可以咩？为什么它一定要闭起来啊？这应该是 continuity 的问题吧？
哦。
但是为什么它不可以是一个点呢？它如果是一个点的话，你又没有用了。
你不给他 constant on boundary？
可以，我给他了，但是我给他过后会不会有 contradiction？如果没有的话，就解不到。
有哦。
有没？
有啊。有没？没有吗？
所以为什么没有呢？
因为它是bijective的。
是吗
bijective，然后呢
有 bijective 的。
又怎样呢？
所以它的，如果一个点对，如果它的 对，因为只是一个点的话，它们是不一样的。
好的，后面我们不可以有
不 injective，
对
不 injective，对。然后下一个可能你 argue 是为什么它不可以是一条线吧？这应该是用 continuity 吧？
因为
没有这个好像也是不会产生问题，不然这样的话一个点会送到2个点去。
对，
没有啊，它可以来 open 啊。
没有，你这个圈是 close loop 的嘛？
对啊。
你随便拿一个点。
没有，这个是跟 continuity 有关系应该。
OK，
因为它可以这样吗？可以这个点到这边然后开吗？没有问题啊。
因为它 continuous 问题，这里是 connector，这里不可以有 jump，
这样
就不可以来前后点莫名其妙跳去海点。
就是说，或者说这里的 open set。OK， 或者说这里的 open set 过来这边就不 open 去，被分掉。应该。像上次我们说这个啊，
一样的球变2粒球去，是吧？是这样意思。
就上次我们说这个跟这个不可以是，这样的话它一定要一个圆圈，如果是圆圈的话就可以了，它就不 connect 的。
对哦。都是，好啊？什么？都是，
这么不对，这么没有睡，
是不都？
紧张要考试。
没有啊，我2天，因为我2天读了200面的课本。
那你昨天讲你没有读就突然间又读了200面，
不爽。
怎么读了200面？我的 MA。
我谈着来要不要读哦，然后文昌就讲要读。
我帮别人补习的时候读了一遍。
对，我就边读然后帮别人补习。
到零点后。
那一群没有。
OK，
那些全需要你来补。
所以直线了。
然后
再 B1。
我没问题。
Okay, let's start. So please tell your friend Thursday come to class because we're gonna discuss the exam midterm. Okay, tell your friend to come remind your friend. Okay, to define compactness, we will define another notion first. Again, because this is a topological space, right? The subset of the space is pretty important here. So we're gonna collect a new subset of our topological space such that if this set is said to cover, okay, or we said that it is an cover or covering of X if the union, okay, of elements in script A is equal to X. Okay, so meaning we can write X as a union of AI such that AI in A. Okay, this is just a fancy way to talk about union. Okay, it's just a fancy way to talk about union here. Okay, we can say that if we can write X as a union of some AI subset of X here, I will say that this collection cover, okay, cover, sorry, here is covering, cover X. Okay, so how to cover? Take the union. Okay, it's like you patch things together, cover it. Okay. So one thing might not be enough, so you take more things to cover. But obviously, you can put your X into your collection of A, right? For sure, you can cover one. Does it make sense? One of the element could be the whole space. Then definitely you can cover. Okay. But this is not the trivial thing we want to think about. Later we will show that it's some more property from discovery. Okay. So in case let's say we don't want to take the whole collection. We just take a sub collection of A here. If it also cover X, we will call it a subcover. Okay, so meaning you don't need every AI. Okay, just pick few of the AI. Few union to become X, we call it subcover. Okay, no? Okay. So I mean, in principle, these sub collection will form collection also, right? Yeah, but the point here is if we start from a larger collection, okay, we found that a smaller collection actually is enough to cover, then we'll say that it is a subcover. Okay, coming from this A here. Okay, so but the more important thing is about open covering here. So meaning we don't simply cover our set X, we want to cover it using open set. Okay, if all AIs are open subset, okay, then you can write it as a union such that the union is equal to X, then we call it open cover. Open covering or open cover. Does it make sense? Okay. Okay. So next. So we're gonna define compactness now. So a topological space XT is compact. So this one is very important. A lot of students have understanding, misconception on this. A topological space is compact if for every open, you need to check for every open covering of X contains a finite sub collection that also cover X. Okay, I give you a misconception question problem here. For example, okay, so this one is a Sala or wrong. Okay, Sala is BM. So wrong, wrong from section here. For many people will tell me that, oh, 01 is 01 is compact actually, but let me pick someone that's not compact. Let's say R is compact ma. Okay, how is it compact? Because R can be written as negative infinity to 0 union. I cannot start from 0 to infinity, right? Otherwise, there's no 0 point. So I just put -1. Okay, finite cover. Yeah, done. Good. Salah, 0分. What's the definition doing? Every open covering. 怎么我一直加 n 进来 Over every open covering of X containers finite subcover. You need to check for every. This is only one of it. 这个只有一个. You need to check every. You need to check every. Okay, every open covering has a finite subcover here. Every. Every how to check? 你问我我也不知道，其实很难的，要证一个东西是 compact 的话，其实是很难的。But to prove something is not compact 呢？来，再问Joshua。If you want to prove something is not compact 呢 what do you do? This one is a discrete math question. Not compact, how to prove? For every become what? There exists an open covering that doesn't have finite subcover. How can you do that? You find one cover such that finite of them cannot cover. What is the relation between the whole collection and finite collection? Maybe you need to remove some of the open set. So meaning what? If you remove some open set, the union cannot be the whole X already. You are missing point already. Okay, this one is easier to do than checking every open covering. Okay or not? Okay, makes sense? Okay, so first thing we're gonna show is R is not compact. Okay, can you try and think about it? Give you 2 minutes. Find one open covering that doesn't have a finite subcover. 等到了? Well, okay, so let's try. How about wait for 1 minute first? Let others think first. Think about one covering, okay, that doesn't have finite subcover. There are million of solutions to this question on million. Okay. There are 28 of you here. Should have 28 answers here. Huh? Let's try and find a cover. So open set in R is what? Last time we proved, right? It's just some open interval. Okay. So try and find some union of some open interval such that it doesn't have finite subcover. Actually, this thinking is very geometric, I mean topological. So try and draw it out. How do you cover it? Okay, how do you cover it? Okay, so if you cover this, you must missing some point, right? So you might want to think, can I cover like this? Okay, so can you think of a systematic way to cover it? Okay, 来, Adrian got answer. Huh? Union of minus KK. Okay, got any other answer? Any other attempt? Yeah, it's a reparametrization of this one. It's okay, but I don't want KK plus 2, huh? So union of negative for double, negative infinity. Doesn't make sense, eh? Or you want to split it up? Can we write in that way, huh? Huh? Oh, okay. I think I know how to write your thing. Okay, so can you tell me what's the set first? I mean, sorry, what's your open interval? K to K plus 2. Okay, one way to solve your problem, right? Is again, I want to use K from, let's say, you want to include 0, is it? You want to include 0. So 0 to infinity of minus k minus 2, enough or not? Is this what you want? Swap these two. Is this what you want? You mean k from 有人从 negative infinity 开始算的吗？你算给我看一下，你从这个减 infinity 的算回来给我看，你算回来 make sense 吗？你算回来给我听啊，你算给我听啊。不确定哎，我不觉得哎，你从啊？Oh yeah, oh yeah. 对。So there's an advanced way to do that, So there's an advanced way to do that, I think. So K and Z, yeah. So this is like a doubly, how to say, doubly infinite. Yeah, go infinite on both sides. Okay. Yeah. 1K. What do you mean? Oh, okay, so same thing. Same thing. Yeah, because if you pick the right end, but midpoint is the radius one both. Any other answer? Want to try here? Any other answer? Or any other attempt? If not, then we discuss these two. Is R itself a covering? Uh, sure, yeah, yeah. R itself is a covering, but it's also a finite subcover already. Not very helpful here. We want something is not doesn't have a finite subcover. Okay, so yeah. What what do you mean? Mm-hmm. Mm-hmm. Oh, you mean okay. So you mean like this, like this? Is singleton open or not? No, it's not an open set. Okay, so let's discuss about these two cases. So let's name this one, then these two. Okay. So what is one doing here? Anyone imagine what is one doing here? So what's the first set you start with? Negative 1 to 1. Okay. Second, negative 2 to 2. Okay, can you start seeing the pattern here? This open set is growing. Okay, it's growing. Does any finite collection of this growing set here cover X or not? So how do you think about this question? We need to have just finitely many of them. Okay, finitely many of them means what? One possible way is maybe you just take 1 to some n. Okay. The other way is maybe you don't take everything 1 to n. You just take finite, so you jump. Maybe I take even number one up to some 2n or odd number one. Or I just simply jump. K goes to 1, K goes to 3, 4, 5, 6. But all these cases, it is just finite. Meaning what? There must be a largest, and you take. From the finite collection of these, there is a maximum K. We'll call it N. Okay. So there's a maximum you will reach here. No matter how you take it, because it's finite, right? So you should end with some maximum N. Okay, so maximum K such that what? Such that R is equals to union of maximum. Okay, so this N such that R is the union of, how should I write it better? K equals to 1 up to N. Let me think. Is there a better way to say this? Okay, let me put it this way. N is the largest K such that the open interval minus K to K is inside R, such that this R here is equals to some union of, let's call it I equals to 1, let's say to N. to, let's call it, how about call it Ni? No, not good. Call it sum M minus Ki to Ki. Is this good? Yeah. Okay. So meaning if I write it as some finite intersection, finite union here, okay. And then what's this Km here? This Km here will give you the largest, okay, which we call M here. So is it enough or not? Enough to cover R? Why not? Because we won't have n plus 1 inside this union. So in particular, maybe you want to look at this minus, sorry. Yeah. So in particular, you want to look at this minus n minus 1. It's not in there. Okay. Yeah. Yeah. Do we need any theorem for the existence of this number? Why this number exists? Or why the larger number exists? Huh? Archimedean property, right? Yeah, you can use Archimedean property to show that this number. Okay. For every epsilon, you can find a number. Okay. How about this one? Does this work or not? Okay, let's draw this picture here. Let's draw this picture here. So let's start from 0 again. So let's look at it one by one. Look at the first one. K to K plus 1. So what is it? 1 to 3. So let's say 1 to 3 here. 2 leh? 2 to 4. Okay, so 2 to 4 like this. Okay, so you can see that the next one is 3 to 5 like that. Okay, so overlapping. Yeah. So let me draw a bit apparent. So 1 to 3, 2 to 4, and then 3 to 5, and so on. Does it cover finish? So let's try first. So how about the other one? You start from where? 0 minus 2 to 0. Okay, so minus 2 to 0. And then if k equals to 1, minus 3 to minus 1. Okay, and then like that. Okay. So there's one part haven't covered. How how to add this part in? This one count from -1. If we count this from -1, so we include one more thing in. So we add in -1 to 1. So we add in -1 to 1. But 1, how about 1? How to cover 1? 0 to 2 inside there or not? So, oh, we don't just add 1 point, right? We add 2 points here. Just now we start with 1. So when k equals 0, we have 0 to 2. Okay, good. So we add, so it's covering all the R already. Okay, good. Okay. So why does this doesn't have a finite subcover? You cannot tell any of the interval. Wow, this accusation is very harsh. 一点都不可以拿走哦，真的假的哦？你拿掉一个。Okay, let's try take one of them off, right? So which one? Let's go from this side here. Let's take one of them off. Okay, for example, let's take 1, 2, 3 off. So the argument is 2 is not in there. Okay, so you need to show for general one, for general open interval here, you take it off. Who is not in there? Whenever you take k to k plus 2 off, who is not in there? K plus 1. You need to argue why k plus 1 is not in there. So meaning k plus 1 only live in k to k plus 2. And then the other two beside it shouldn't contain K bar. You need to prove in general. Okay, so what you want to show should be claim is you cannot take off any one of the open set. Okay, otherwise inside K and K plus 2. Okay, so how do I put this? Okay, don't put this first. Okay, so the claim is you cannot take off any one of the open set. Why? Because if you look at the midpoint, okay, if you look at the midpoint of these two open interval here, maybe to prove this claim, right? Maybe you need this lemma, right? So what's this lemma here? The midpoint of k plus 2 and minus k minus 2k. First one is for all k greater or equal to minus 1. The other one is for k greater or equal to 0. It's not in the other open interval. Okay, is this what you are claiming? Okay. Okay. Okay, does it make sense? Okay, so for example, if you take off this interval here, right? So you look for the midpoint, and then this midpoint exactly lie in the meeting. Can I say meeting? A boundary, okay, boundary of these two open interval. But this two open interval doesn't contain the boundary. Okay. Yeah. Make sense, huh? Okay, try and show this. Okay, so this is not compact. Okay. So in this note, right, if you look at it, I want to show my drawing only. You go back and read. But you also can show that what is it? Okay, the complex number, right? Okay, which has the similar topology as R2, okay, induced by this norm here. Also, it's not compact, okay, by building this infinite open cover here, okay, BI. So what is this BI here? This idea is like what Adrian do just now. You make your open interval bigger and bigger and bigger and bigger and bigger here. Okay, so this BI here is a ball that center at this origin. Okay, and then you just look at the drawing radius of this ball. Concentric ball, we would say. Okay, with the same center, concentric ball here. And I use this to show that it is not compact. Okay, yeah. So you can think that you cannot use a finite subcollection to cover it. Okay, and then last, before we jump to some theorem here, in fact, later we'll show that the closed interval is compact. Okay, but the open interval 0, 1 is non-compact. So in this example here is we can see that there's non-compacting leads. Non-compacting living inside compact set. Okay, it's possible. Okay, it's not that the subset of compact set must be compact. It's not the case. Okay, you might have non-compacting leads living inside compact set. Okay. So this one is not compact using similar argument just now, but this one we haven't proved yet. Okay, later we'll prove to you why closed interval is compact. Okay. Next theorem. So the following are equivalents. Okay. So X is compact if you have a collection of open set and every finite sub collection fails to cover X, then C fails to cover X. Okay, so this is actually the contrapositive of the compactness, right? So compactness says what? For every covering, okay, that can cover your X, then it has a finite subcover. If every finite subcover, okay, doesn't fail to cover X, then C also should fail to cover X. Okay. Can you see or not? It's a contrapositive. Okay, so maybe let's write down in a logical statement here. So for every C, okay, if and X equals to the union of C, then there exists Ci in C such that union of I equals to 1 to N equals to X. Okay, I'm a bit cheating here. 我教过你们这个 notation 吗 ？Union of 一个大 set， 没有教过你的 notation， 还是你从哪里有看过这种东西？啊 ？Sorry？ 这 notation axiom of choice 哦，有啊，好像有啊。哎，有吗？没有吧？axiom of choice proof 里面有，我没有印象哦。你可以 show 给我看一下，下次。But what is this doing is union of all the I of Ci. So how to write these? How to write this? 我想一下，OK 没？OK，不然再写一个比较相近的，but union all the Ci such as Ci in C。从这样你可以猜出这是什么意思啊？就出来。Not quite, not quite, not quite, not quite, not quite, not quite. We are not quite. Yeah. So you actually union all the C, such as C is in C. That's it. 这样子。When you say C inside a union, you are viewing C as an element. We are not doing that. We are actually like matching this C. So inside this union, right, all the elements are coming from this C. The way you put it just now is like C is an element. Okay, so this union of I didn't put any index. Not that didn't no index here. Meaning we are unioning all the set inside this thing. Inside the set here. Okay. So if you like, is this union all the set inside this? This one is what we introduced to you last time. But yeah. Okay. But do you think that this is a good shorthand notation or not? 你觉得这个 shorthand notation 好吗？啊，不用写这样多东西，你看 C 是 repeat 的，都没有什么用的感觉。哪一个？哪一个？啊，有有什么？这个哈，I 什么意思？I C 哪一个？这个script C。Yeah。对，没有 I，没有 I，是没有 I 啊。有 I 的 version 是这样子的东西。So you might see that 哎，这个好像有一点 redundant 其实。So in some of the book they will use this notation. Okay, union of collection of set is just a union all the set. 我不用再跟你讲 index 啊，跟你讲也是没有用的，反正我就是要全部在一起，对吧？Okay, does it make sense? Okay, so this is the contrapositive lah. So these two are equivalents. Okay, if you are a collection of open set, okay, and then if you are a collection of open set, and then the union, okay, you can cover X. It implies that there's a finite number of them that can cover X. If you cannot do this, cannot do Q, then P also doesn't work. Okay, so this is the equivalences between these two. Okay, does it make sense? I check. Oh, sorry. 对，我忘记去，谢谢你。Yeah, otherwise 不知道在 union 什么东西。Okay, good. Okay, 还有吗？还有问题吗？ Okay. And then third equivalent statement is, wow, 这个很 interesting because we are phrasing compactness using open set here, right? So because we know that there's a complement between closed set and open set, right? So we can also phrase it in closed set. So let's say if F is a collection of closed set such that every finite sub-collection F1 up to Fn has non-empty intersection. Okay, so meaning if you take closed set, collection of closed set inside your compact set, and then you look at finite intersection, finite collection of them, they intersect, then what happened is, if you take everything intersect together, okay, or just now we 会不会有一点你们会 key 笑吗？你的这个 F 站着，这个 F 是站着的，这个 F 是飞的 ，OK， 我要小心一点 ，OK， then this thing here, this intersect also non-empty. This is very interesting property 你知道吗？因为 finite 的 intersection doesn't imply every the whole intersection， 不一定啊。还记得我们上次做的东西吗？我想一下，上次做我们有没有 ？Yeah, sure. So if finite intersection, right, doesn't imply when you take intersection of everything, it should be non-empty because it's way more close set inside collection. What's the worst thing? Is like you will get empty set from your intersection. But if it is compact set, right, closed subset of compact set, right, you also will get non-empty element here. Actually, this non-emptiness is the thing that you want in your limit. This non-empty guy here is the limit that you need for your string value theorem, for your more theorem lagi. But it's the thing that when you ask for limit inside compact set, this is what you need. Okay? Intersection of arbitrary closed set is non-empty. Okay. Okay, I think a very interesting one, I think is 2 to 3 ba. Okay, to show 2 to 3. Okay, 1 to 2 is just contrapositive. 2 to 3, how to show this? Okay, let's try. We straight away jump from 2 to 3. Let's do this. So let's see. Oh, let me think. How should we put this? Or how about actually 1 to 3 lah. Let's do 1 to 3. Okay, so in one, right, you have union on C equals to X. Okay, it depends on how you view 1 and 2. Actually, they are the same. So let's use the 2 language to talk about it. Okay, let's say you can write X as a collection of open set coming from C. Okay, so something wrong here. This is C. Then what does it mean here? So if you take X, taking away this set here, what do you get? And what is this? Actually, this is X, take away X, right? And then this is just empty. Okay. But on the other side, what do you get? On the other side, what do you get? You are complement of union. Meaning what? Intersection of complement. Okay. So can you see something from here? What can you see here? What can you see here? What can you see here? From this equation here, how do you deduce what you want? So you have an intersection of closed set, right? So if you have an intersection of closed set, okay. So let's look at C, okay, the statement you want. Collection of closed set, okay. But collection of closed set, you can think of it as a collection of collection of closed set here. You can think of it as a collection of complement here, complement of open set, okay. And then what? Such that every collection, finite subcollection of this have non-empty intersection, then it must be non-empty. So let's prove the contrapositive of this statement. Contrapositive says what? If I take the intersection of all these things to be empty, then the finite subcollection must have empty intersection also. Okay. Okay. So you see here. So if you take arbitrary f here, okay, and then you form this intersection of C here, intersection of a complement or open set, okay, such that it is equals to empty set. This means what? This means that the union, okay, this means that the union of these open set should be the whole space here. Okay, does it make sense? Okay. Okay. Then from here, how do you deduce every finite sub collection of these closed set has empty intersection? Eh? Any idea? Let's finish this before we end. How? Let's say this is just some draft. How about let's fix some let's fix this. So let's do 2 implies 3, 3 implies 2. Okay. Okay. I think maybe it could be some maybe overload a bit. So let's do it step by step. This is like how you study at home, right? Huh? Do you get stuck? Idea or get stuck or not? Idea. Do you get stuck at home when you study? So what do you do? Yeah. Should I demonstrate how to use ChatGPT? Or you demonstrate for me? Okay, without using ChatGPT, so what should you do? So just bring these two statements close together first. 怎么有人一直开门，一直开门呢？对啊，当然没有到时间，那么一直开门。他们要考试是不是？Okay, so we want to show these two are equivalents, right? 我们不要这样贪心了哈，一步一步来，OK? So left to right, right to left, okay? So if from here to here, what do you need to assume here? Okay, you need to assume this whole thing here, right? And then the last part is your goal. Okay, so assume this and then prove this. Okay, so you start with what? A collection of closed sets. Okay, such that every finite subcollection has non-empty intersection. Okay, then somehow you need to use this assumption here. Okay, to help you prove this goal here. Possible? So here is assumption. Here is assumption. and then green part is gold. Okay, is it possible or not? Hi Larry, how you start? Such that, let's say we call this assumption one. Such that assumption one is true. Okay. So if you're gonna use this assumption, let's say call this assumption two. If you want to use assumption two, right, you must create open set. How to cook out open set here? Sorry? Complement, right? Because you have closed set now. So one thing you can think about is to take the complement of the closed set inside this F. Okay. But to trigger this assumption, so to trigger this assumption, right? What do you need? You have assumption inside assumption. Okay, you need that every finite subcover fail to cover X. Subcollection, not subcover. Subcollection cover X. So look at or what? You want to try? Want to try? Try right now. So consider because it's every, right? It works for every, right? Just consider F1 is okay. Yeah, sure. Okay. Consider F1 intersect F2. Okay. It should be non-empty, right? Okay, by assumption one. So this F1, F2 should come from, so that exists F1, F2 coming from F. Yeah, no, it's not empty. Yeah. Okay, then 这么好。哎，sorry. Okay, thank you. Okay. Then. How to see it? Correct. So if you take X minus F1 union X minus F2, but what is this? This is the intersection of, X intersect with 有写错嘛？怎样 combine 呢？So 刚才是 union Okay, correct. So this one is equal to X take away F1 intersect F2. Okay, but this one is non-empty, right? So this means like you take out something. You really take out something. Also, this means this is not X. Okay, so it means what? So it means that X minus F1. So this collection fails to cover X. Okay, but to trigger this assumption, you need every finite subcollection. This one is just one of it. Can you do it for every finite or not? No, you need to consider more general F1 up to some Fi. Then the same argument works. You just put more I here, Fi here only. Okay, not. So generalize. So put here. So this one. So I'm telling you how to do max on your own. So here, let's say argument one. Not that we can generalize. Obviously, you don't do this in your assignment. This is for your own working only. In your assignment, what you do is you should straight away tell me that for the finite intersection case, we can do this calculation. Okay. Then what? Then x take away f such that f living in this script f here fails to cover x. But fail to cover x means what? Fail to cover x means what? Fail to cover x means if you take the union, okay, of all this set, union of all this set is not equal to x. Okay, so this implies that the intersection, okay, of f in f is not empty. Okay. Okay. Does it make sense? Okay, and then I think you should realize that we can go backward. All these argument we can go backward. Okay. Any question? 有问题吗? If got problem, we bring to next class. Okay, we have to move now. Okay, thank you.